Thanks for inviting me. Sorry for all the technical trouble.
No, that's okay.
Spin threefolds. Okay, so let me just give you an idea. Let me just start with saying a little bit about reviewing classical Donaldson Thomas invariants and how they arise. So that'll be the first top, the classical DT invariants. These arise from virtual fundamental classes. Okay, and then I'll explain how you get quadratic enrichments of these. So these give you values in quadratic forms, which enrich the DT invariants, which are integers. And then I'll mention some work of Annelos Viergever, which are some computations for the case P3 and a conjecture. Okay, so can everybody read what I'm writing? Is that okay?
Yeah, that's okay. Actually, I increased the volume of my my microphone. Now I'm hearing you very well. There is no problem.
Very good, very good. All right. So so the way you get the classical case the ones I want to talk about are the following. You take X to be a smooth projective threefold, let's say over the complex numbers, and then associated to that, we have the Hilbert scheme. This is, length n, dimension 0, closed subschemes. Really, it parameterizes flat families of such. Okay, so that's a fairly large scheme. The dimension, it may have many components. It may be rather complicated, but in any case, you can associate to this. This is from work of Thomas, and then Baron Fontecchi, and also Thomas, or Huybrechts, rather, get it in the right order. They associate to the Hilbert scheme. Thomas originally did this, and then it got kind of refined in a more invariant, sort of derived category version by Baron Fontecchi, and then Huybrechts and Thomas made it even nicer. You get a so-called perfect obstruction theory. On the Hilbert scheme. So let me just call that phi dt Donaldson Thomas n, or maybe it's really Thomas is maybe better. Just call it phi t n. And what this is, it's a map from essentially a two-term complex to the cotangent complex of the Hilbert scheme. Whatever, this associated to this, you have a virtual fundamental class. And the interesting thing about this, there's a general theory. The virtual fundamental class associated to a perfect obstruction theory in this setting, the classical setting, lives in the Chow group of this Hilb n. And what dimension? The dimension turns out to be 0, but in general, the 0, it's really in dimension this is because the virtual rank of this complex is 0. In general, if you have a perfect obstruction theory where the source complex has virtual rank R, then you'll get a cycle of dimension R for the virtual fundamental class. But now X is some smooth projective, is some projective variety. Its Hilbert scheme is a projective variety. So you have a push forward map. There's a push forward map to, spec C. So you can take P lower star of this thing and you get a number. That's the DT invariant. Pushes forward from Chow 0 of Hilb N to Chow 0 of spec C. Cycles of dimension 0 mod rational equivalence on a point. This is just Z. So that's the DT invariant. So I'll say a little bit about how you get these constructions, but let me just say, then Malik, Nekrasov, Okonkov, and Ponderapande consider the generating function for these things. And they also made a computation. They considered this and they computed this for X toric. So if there's smooth toric threefold, so in other words, P3, P1 cross P2, not too many other things, P1 cube, various other things, but a fairly short list of these things. And they found the following thing, which they made into a general conjecture, that this counting function should be given as a certain combinatorial function, the so-called McMahon function, evaluated at minus t, raised to a certain power. You take the degree of the third Chern class of the tangent bundle of X tensor the canonical bundle. And they verified this in the toric case. And then this was later solved or verified in general. So in other words, for a general smooth projective threefold by Jun Lee, and then also by myself and Ponderapande. Okay, so now we'd like to get these quadratic versions of this. So maybe I'd like to say a little bit about how you get quadratic versions of these constructions and the computations that Analos made in the case of P3. So let me say something about that. So what's the construction of this virtual class? So let's just take a more general setting. So you take a Z, there's a general construction for stacks, but let's just work with schemes, because the nice thing about the story for Hilbert schemes is that it's just a scheme, it's not a stack. You also have the situation for moduli stacks for stable maps of curves and various other moduli stacks. But the theory in the quadratic setting is sort of at its infancy in the stack setting. But let's just do the scheme setting, which has a nice quadratic extension. So we take Z to be some K scheme, finite. It doesn't really have to be over K, but let's fix some K scheme, finite type. And we have phi, our perfect obstruction theory. The perfect obstruction theory. So what that means is essentially we can even take this to be quasi-projective, because we're going to be doing it for the Hilbert schemes, which are projective. And it means you can assume that this is just some two-term complex. on Z, and the phi has the property, so I'm, sorry, F1 to F0. I'm going to use homological notation. So the assumption is that H0 of phi is an isomorphism and H1 of phi is surjective. So that's a perfect obstruction theory. And then what you can do with that, there's first of all, there's two steps to construct this virtual fundamental class. So this will live in Chow R of Z, where R is the virtual rank of this guy. So this is a two-term complex of locally free coherent sheaves. So the rank is just, this is in other words, the rank of F0 minus the rank of F1. These are locally free. So what you do is there's two parts to it. The first part is you just have we assume, since it's quasi-projective, Z sits inside as a closed subscheme of some smooth K-scheme. And then associated to this, we have the normal cone. So this is a cone over Z, and it's just, by definition, it's just spec of the over OZ of the direct sum of the powers of the ideal sheaf modulo, the next power. The ideal sheaf of Z. And there's a canonically defined fundamental class on this thing. It turns out that this will have, let's say this Y, let's give it some dimension. Let's say N is equal to the dimension of Y. This will be a pure dimension N scheme, and we'll have an associated dimension N fundamental class. Sorry. And let me say, there are various ways you can do this. Oh, somebody's in the chat, I guess. That I missed? I think it's better. Okay, good. So there are various ways you can do this. One way is it's a scheme, and you just take at each generic point, you take the length of the non-reduced part, the thing that measures how non-reduced it is. But there's a somewhat more canonical way of doing this, which I want to describe for the purpose of generalizing to the quadratic case. So the way you get this cone is it actually lives as a principal Cartier divisor on the so-called deformation space of Z in Y. So what is this deformation space? You just take the blow-up along Z cross 0 on Y cross A1, and then you remove the sort of uninteresting part, which is the blow-up of Y cross 0, of Z cross 0 in Y cross 0. So if you just take the blow-up, so this thing lives, of course, maps to Y cross A1. And just to draw a little picture, here's your Y cross A1. Here's your Y, here's your Z. You're blowing this up. So when you blow this up, this will be Z cross 0. Here's the 0 in the A1. When you blow this up, you have, this will be, of course, Y cross 0, this fiber here, Z cross 0. You have the proper transform of Y cross 0. Let me put a little bracket over here. And then you have the exceptional divisor E living over Z cross 0. That's what happens over 0. And then everywhere else, it's essentially an isomorphism. So, and then the deformation, that's the blow up. And then you just remove this part here. And you see what happens is that this deformation space, really gives you a deformation. So over 0 in A1, you just have the, it's exactly this normal cone. And if you look at it on the complement A1 minus 0, it's just y cross A1 minus 0. Okay, and this cone as a scheme is just equal to, it has the ideal sheaf of this cone is just T, where this A1 is spec KT. It's the parameter on there. And so you can define the cycle here by just taking the divisor of T. That will automatically give you the multiplicities. Okay, so that's what this cone is. That's the first ingredient. Any questions about that? We're good? Okay.
No, that's okay.
Yeah. So the second ingredient is you have to, so you want to get this cone is sort of use some intersection theory. You notice that this cone didn't use anything about the perfect obstruction theory yet. So we want to bring that in. So we have our perfect obstruction theory. And it's a fact that when you're mapping to this cotangent complex, but you can just pass to the truncation in homological degree bigger than or equal to 1 of this guy. And it turns out this has a very explicit expression. It's just the ideal sheaf on Z modulo its square. It's the usual map going by, the differential to the pullback of the 1 forms on Y. All right, I is the inclusion of Z into Y. So this is an explicit description of this thing. And the condition, this is my phi, and the condition that H0 of phi is an iso and H1 of phi is surjective is just saying that you can form the following complex. You take F1, and of course you have this map to F0, but you also have the map phi 0, your phi 1 rather, maps from F1 to the ideal sheaf. And then again, the ideal sheaf maps to the pullback of the differentials, but so does F0 by phi 0. So you have a map here. Okay, so you get this complex, and this is exact. So let's call this map gamma here. And let's take Q to be the kernel of gamma. So we have this thing here becomes an exact sequence. And then we have a surjection from F1 onto Q. So you can split this up into pieces. And now you have this construction. If you have some coherent sheaf on any scheme, let's just say on Z, then you can associate to it the scheme, the cone, the abelian cone. You take V of E, which by definition is just spec of sim star, the symmetric algebra on E. Let's say this is a coherent sheaf on some W, then this will be spec over OW of this thing. So this is the so-called abelian cone associated to this coherent sheaf. If the coherent sheaf is a locally free sheaf, this is just the vector bundle whose sections are the dual of your original locally free sheaf. And it's just a generalization of that. And so this is some contravariant functor, so you apply it to this sequence. And when you apply it to this guy here, of course, it just gives you the tangent bundle. So you get a sequence that looks like this. And then you have this V of this iz mod iz squared plus v of f0. Now, this is a vector bundle here. This v of f0 is a vector bundle. Well, let me just write it, since this is a cones, let me write it as fiber product over z, and then goes to v of q, and that will be a surjection of abelian cones. And on the other hand, this surjection here induces a closed immersion of this v of q into the vector bundle v of f1. And similarly, right, you have the, sim star is the direct sum over n of sim n of iz mod iz squared. And this maps onto the direct sum of iz to the n mod iz, to the n plus 1. That's a surjection. And so by taking specs, that gives you a closed immersion. Let's see, sorry for the splitting the pages. You have a closed immersion of spec of this thing, which is your cone. And of course, you have cross this v of f0. Okay, so you have this closed immersion and this closed immersion. And it turns out you can show that this is now a subbundle of this cone. The restriction of the tangent bundle is a subbundle, and this inclusion here actually factors through an inclusion into this fiber product. So you can show this. So you can then take quotients. So what does this do? Let's call this product here, we'll call this D, and we define D ver to be this D modulo this sub-vector bundle, this thing here. So this is just, you take this cone, cross with this vector bundle, and then mod out by the sub-bundle I star of ty. Okay? And now, of course, when you take the quotient, you're taking this guy here modulo. So this thing injects into this quotient, which is just the VQ. So this injects into the VQ, which in turn injects into the V of F1. Okay, so the picture looks like this. You have your D. Your D, of course, projects onto the cone. And the fiber here is just this vector bundle. So this is a nice, smooth map with fiber, a vector bundle. And it also projects in the other direction to the quotient. And here the fiber is this other vector bundle, I star of ty. Okay, so, and this guy, so this guy here, remember, has this associated fundamental class. And this map, let's call this P2 and P1, these are both essentially vector bundles, or not quite vector bundles, but they're certainly smooth maps. So the pullback, we can take P2 star of this thing, and we can call that's the fundamental class of this D. And the other hand, the Chow groups here are isomorphic to the Chow groups here by pullback. From Chow, let's say A of D ver is isomorphic to Chow A plus, well, the dimension of V, right? This is a bundle of rank dimension of V, Chow plus N of D. So whatever my class is, let's see. So let's see. So what's the dimension? This thing here has dimension N. This thing will have dimension N plus the rank of F0. And then you lose dimension again. So in this guy, we'll take A to be n plus the rank of F0. Sorry, we'll take A plus n to be n plus the rank of F0. So that says A is equal to the rank of F0. So we have a fundamental class D ver, which maps to the fundamental class D, which we got from the fundamental class of my cone. And this D ver lives in Chow, rank of F0 on D ver. Okay? So that's where the rank of F0 comes in. But let's see, we're looking at a quotient. The D ver, remember, sits inside, has an inclusion, let me call it I ver, into this vector bundle for F1. And now we have, this is a vector bundle over Z, so we have the zero section. Let me just call it 0. And so what we can do is we can take the pullback. This may be highly singular, but the 0 section is a LCI morphism. It's a regular embedding. So there's a nice pullback map. And so you can take this thing here. And where does this live? Well, it will lower the dimension by exactly the rank of this thing. So this lives in Chow, rank of F0 minus rank of F1 on Z. And this thing is exactly, this is equal to this virtual fundamental class. So that's the definition. Okay. Any questions? I mean, it was maybe a little lengthy, but it's a two-step procedure. You construct this cone. You have the choice of the closed embedding, so that's already a choice. What Behrend and Fontecchi do is they say you define the stack. You take the cone modulo the tangent bundle of Y, and they show that that thing is actually an intrinsic object. Doesn't depend on the choice. And we, in this construction, we ended up taking quotients by the tangent bundle, but these are real quotients. They're all quotients as schemes because it's a subbundle. And the advantage of this is you're really doing the Behrend-Fontecchi construction, except you're staying in the world of schemes. You're not having to move into stacks. So if you're happy with stacks, it's not much of an advantage, but if not, it's a little more concrete. And so based on the Behrend-Fontecchi construction, you can see that this is actually independent of the choice you made of your closed embedding. That's the theorem. So it's a well-defined gadget. So any questions?
Yes,
Yeah.
I lost the connection with the first part of your talk when you ended with McMahon function.
When
then,
I say it again. Just repeat the question.
The relation between the second part of your with the first part that you ended up with the McMahon function.
Okay, so maybe I make so here the first part was the construction of this cone and its fundamental class. And then the second part, this D and this D ver, these two rely on the phi. So this thing here is essentially independent of the perfect obstruction theory. It depended on a choice of Z inside a smooth variety, Y, but sort of you can fool around a little bit and say it's actually a completely intrinsic thing. It's a so-called Behrend-Fontecchi intrinsic normal cone. That has nothing to do with the choice of a perfect obstruction theory. But with the perfect obstruction theory, you more or less, I mean, what it's saying is up to this zigzag, you can put the cone inside a vector bundle. Really what you're doing if you like, you're putting the cone in the quotient vector, the intrinsic cone is going in the quotient vector bundle V of F1 modulo V of F0. And that's why you get this difference of the rank. That's the rank of the so stacky vector bundle where this intrinsic cone is sitting. And then you pull back by the zero section to get this guy here. So the two steps are you have this cone, doesn't depend on the perfect obstruction theory. And the perfect obstruction theory essentially gives you an embedding of the cone in a, or something related to the cone, that's this d-ver inside some vector bundle, and then you pull back that class by the zero section.
Okay.
Does that answer the question?
Yeah, I think we did.
Okay.
And so another question. So
Yeah.
how do you say that, like, this is actually, I mean, this can be the Euler characteristic, like the Euler class for like some nice
Oh,
cases.
okay. That's a great question. So here's a special case, an example. You have your Z. Okay, you don't start out with the Z. You start out with the Y. And you have some vector bundle V on Y. And you write V as, say, V of some locally free sheaf V. Okay? And let's say this V has rank, I wrote down just so I guess, let's see, what did we assume? Rank M. Let's say V has rank equals some number M. And we want the Euler class of this thing. So in this setting, we're working with the Chow group, so it's the top Chern class. So what does this have to do with Cm of V? That's your question, right?
Yes.
So
Yes.
it's a refined version of Cm, because if you have a section of a vector bundle, then the class of the top Chern class is in some sense represented by the pullback of the zero section by the given section, which would be correct if the original section has intersection codimension M with the zero section. But if not, you just get some cycle supported on the zeros of your given section, but it still lives in something where, see, if now Y has dimension N, then this thing is living in Chow M of Y, which is Chow N minus M of Y. Okay, but let's say we have some section S here, and then we'll let Z just be the zero subscheme of the section. Okay, so what you can do, you can take I star, so the section S gives you a map of V onto the ideal sheaf of Z, right? So this is like S dual. And then you can apply I star to it. You have I star of V, let me just call it S bar V going to IZ mod IZ squared. Okay, so let me write it a little differently. You have IZ mod IZ squared. You have this S bar V, I star V. And then, well, we still have this map D to I star omega Y. And we can just say, well, I'll just repeat it, take it to be equal. And this is just the composition to make the diagram commute. And when you do this, what you'll get is you'll get this virtual. So if this is now my F1 going to my F0 going by phi. And when you take the virtual fundamental class of Z, this will live in, well, what's the rank here? This has dimension N, this has rank N, this has rank M. It'll live in Chow N minus M of Z. And it has the property that when you push this forward by I lower star to Chow N minus M of Y, it goes exactly to the top Chern class of V in here.
Right.
So it's equal, if you like, it's the Chern class with supports on Z of V associated to the section S, which Fulton, you can construct that by Fulton's intersection theory, and that's exactly what you get. Thanks for the question. Any
Thank
other
you.
questions? So do I stop at when do I stop here? You tell me. Make a decision.
No, I think we started. You have still, I think, 15 minutes if you want. I mean, we started 15 minutes late.
Okay, so I have 15 minutes. Okay, so let me say a little bit about the quadratic version, quadratic refinement. So it's really what you do is you just feed the two-step construction 1 and 2 into this black box of the motivic stable homotopy category with 6 functors. So I'll be real brief about this, but here's the idea. We want to realize, just to give you some orientation. So if you have, let's work over a field K. This is our base field. And if you take some object here, some E, this is a motivic ring spectrum, let's say, whatever it is, associated to this, you can take any smooth variety X, and you get bigraded cohomology of X. Well, let me just, without going through the whole machinery, let me just give you an example. If you take E to be the HZ, this represents so-called motivic cohomology, then HZ PQ on X is Voevodsky's motivic cohomology. And if you know what that is, fine. If you don't, the special case, which is what we're interested in, if you take 2QQ on X, the H2Q Z of Q is just the Chow group of codimension Q cycles, my rational equivalence. Another example is you can take E to be the spectrum so-called KGL. This represents algebraic K theory, and then KGL PQ on X turns out to be Quillen K theory in degree 2Q minus P on X. So again, if we take this 2QQ part, this is just the Grothendieck group K0 of X. And there are many, let me just give, one more. You take E to be, okay, this is something you're probably not familiar with. You take the Eilenberg-MacLane spectrum on the Witt sheaf. So the Witt ring, the Grothendieck-Witt ring, is the Grothendieck-Witt ring of virtual non-degenerate quadratic forms. It turns out you can define this for any ring and it makes a sheaf. And the Witt ring is you essentially take this modulo hyperbolic forms. And so let me just say this thing on some X is just the cohomology of this sheaf. It's rather a simple-minded object. But in this 2Q part, this is HQ, and you have an interpretation of this thing. You can think of this as codimension Q, I'll call it cycles on X with coefficients. So what's an algebraic cycle? It's a sum of codimension Q. It's a sum of codimension Q subvarieties with coefficients in the integers. Here you take the coefficients, let me call it in the Witt sheaf. So a typical element in here will look like some Z equals some alpha I Zi, where the alpha I is in the Witt sheaf on the function field of Zi. And the Zi's are codimension Q subvarieties. Now that's a typical element will look like that. There's conditions and their relations. So just to give you a rough idea of what that is, the main difference is you have quadratic forms as coefficients living somewhere or other instead of integers. Okay, so once you have this E, you have a Borel-Moore theory. The Borel-Moore theory of E, and you can twist it by an element. So here, X is any scheme over K, finite type scheme over K, and V is something in the K theory of X, let's say derived category of perfect complexes, if you like. So again, what happens in, so let me just give a definition of this thing, just so you see there's some definition. What is this? This will be hom in SH of K of, well, you have the PQ suspension functor. It's like suspension in usual homotopy theory, except you have two kinds of suspension. You have the topological part and the GM part. So there's a topological degree and a weight. That's the P and the Q. You can also suspend with respect to a vector bundle, or more generally, a virtual vector bundle. You apply to this, and you apply this to the unit on X. And then you take the PX lower shriek of this thing, and you take the hom of that into E. So, you know, you have PX is your map from X to spec K. And you have these, you have the usual push forward, and this is the exceptional push forward. Okay, so since I don't have too much time, let me just mention, if you have any map F, then you have a pair of adjoint functors. You have the usual F upper star, which is left adjoint to the F lower star. And then you have the exceptional pair, which is F lower star is left adjoint to the F upper. F lower shriek is left adjoint to the F upper shriek. Where if F is going from Y to X, say F upper star will go from the SH of X to SH of Y, and the F lower star will go in the other direction, and the F lower shriek, of course, will go from the SH of Y to the SH of X, and the F upper shriek will go in the other direction. So just, it's, you know, if you're familiar with the 6 functors on the derived category of constructible sheaves, or any other kind of, these are 4 of the functors. The other ones we don't need. It's the internal hom and the tensor product, but just to give you an idea. So here's a definition, and let me just say, here's the example. In the geometric case, if you take HZ, again, the geometric part would be like 2QQ, Borel-Moore of X, twisted by some vector bundle V. What is this? This is Chow in dimension Q plus the rank of V of X. So the twist, the coefficients here tell you about the dimension, but so does the rank of V. So you might ask, why do I need this V here? Why don't I just take V to be trivial and just use the, you know, the indices? And the reason that you don't see the V looks sort of immaterial, it's because HZ is what's called an oriented theory. The fact that the V just shows up as his rank means it's oriented. And the same thing works for K theory. But it's not true if you take this EM of W, 2QQ, BM on XV. What this is, it's going to be these, let me just say it'll be Witt cycles of dimension Q plus the rank of V, but where the coefficients are in the Witt sheaf twisted by the determinant of V. So instead of looking at quadratic forms with values in the O sheaf, you look at quadratic forms with values in the line bundle, the determinant of V. So it acts, you can think of this determinant V as some kind of orientation bundle. Okay, so with that as a brief preparation, let me just say how you get these. So this is a very quick overview of the theory, but it's basically all set up so you can just follow your nose with the formalism and make a construction. So let's just see, let's apply this to virtual classes with values in E. So you have the same initial data. You have the initial data is we take Z and for simplicity, let's fix a closed embedding into some smooth. And then we have our phi, which is our two-term complex, mapping to IZ mod IZ squared, going to I star of omega y. So the first part is we want to get a fundamental class. That's the essential starting point, but it should depend on the theory E. And it turns out, where does this live? Let me see, get the notation right. Just so I don't, yeah. It lives in E00 Borel-Moore on the cone, but twisted by I star of omega y. Okay, so let's just compare that with the case of the Chow groups. For the Chow groups, the E00 Borel-Moore was the Chow of dimension 0, but now we've twisted by this vector bundle of rank n. And remember, n was the dimension of y, but it was also the dimension of all the components in the cone. So this is actually for E equals hz, this thing here is just Chow n of the cone. So the twist by the vector bundle increases the 0 to an n. And then you just, remember we had this diagram, we had this D going to this C in Y, going to D ver. Here, let's say this is P2, P1. Remember the fiber here was, what was it? I think it was I star of omega, well, it's the tangent bundle. And the tangent bundle was V of omega y. And here we had the fiber was V of F0. Okay? Now, when you associate to this fundamental class, you have a pullback map, because this is a nice smooth map. So you have pullback in Borel-Moore homology. So you can take this guy here. And where does this live? This will live in the same Borel-Moore homology. So it's just you follow your nose here, and the twist gets changed. So what does it get twisted by? You add this sheaf. So that's how the yoga works. And remember, in the case of the Chow group, adding the sheaf just adds its rank. So you're just adding the dimension. And the same thing here, the P1 upper shriek, they're both as an isomorphism. So you have to, it goes from E00 of D ver. So what does the twist have to be to end up here? Well, you're going to want to add the omega y to it. So you have to subtract the omega y here, and this is where it comes from. So by doing this, you end up with this class D ver here. And remember, the D ver sits inside of your V of F0, F1, and then we have the zero section from Z. Okay, and there's a similar change in indices when you take the upper shriek. You have zero upper shriek goes, this is the Borel-Moore theory, to E00 Borel-Moore of now on Z, twisted by F0 minus F1. So you lose not just the dimension, but you lose the bundle, the twisting. And this, so you, and that gives you your Z phi ver E. And that's where it lives. It lives in this group. Okay, so yeah, I'm out of time. Let me just mention one interesting fact. We can take this E to be this EM of W. And we end up, in the case of Z being my Hilb N, where do we end up with? Remember, this theory has the property that it transforms just an arbitrary twist to a twist by the determinant. So where does it end up in? This Z phi ver EMW lives in E, well, we can get rid of this thing. It lives in the rank, well, put it this way. It lives in this EM of W in dimension rank of the virtual bundle on Z twisted by the virtual determinant of the bundle. Now remember, in this case, Z is my Hilb N, and this rank was 0. That was the, I'm taking phi to be the Thomas phi, so the rank was 0. But what about the determinant? Well, we'd like to get a DT invariant out of this thing. To get a DT invariant, you'd want to be able to push it forward. Now, the push forward doesn't change anything. So you'd like to take P Hilb N lower star of this thing to end up in the W of K. That would be, but see, you have this twist by the determinant. So it turns out what you need, the determinant should be trivial, because in order to push forward, you need the determinant also to be trivial. But it turns out you don't need the determinant to be trivial. What you to have this P Hilb N lower star, you just need a choice of this determinant of this F isomorphic to the square of some line bundle, because quadratic forms, you can always absorb squares, is the rough idea. And it turns, so that's the theorem. This always exists for the case of phi t. So you always, this is a so-called orientation. So we can define the quadratic DT invariant of Xn. So for the Witt sheaf to just be this P Hilb lower star of this Hilb N phi t for the Witt sheaf ver. Okay, so that's That's the upshot. And I just want to say that Analos computed some of these. So always exists. I'm sorry, that's not quite right. Assuming there's an assumption here. Sorry, I'm running way over time, but is assuming that we have an isomorphism of the original. This is Hilb N of X. That the canonical sheaf of my X is isomorphic to the square of some other line bundle. That's the spin condition. Okay, so I think I stopped there saying Analos computed some of these. She showed that for X equals P3, of course, the canonical sheaf on P3 is O of minus 4, so that's a square. She showed that these dt of P3n, at least the signature of this thing, you can take k to be the reals, for example, and you have the signature of this quadratic form. This is equal to 0 if n is odd, and it's equal to the following numbers. It's equal to 10 for n equals 2, 25 for n equals 4, and minus 50 for n equals 6. And this leads to a conjecture, which is a version conjecture, that the sum, 1 plus the sum of the signatures of these dt of x, n, and w, assuming that kx is isomorphic to the square of something, should be equal to the McMahon function on minus t squared raised to minus the signature of the obstruction bundle on Hilb 2. That turns out to be the signature of the Euler class of the obstruction bundle. Sorry, get it right. Then I'll stop because I'm way over time. The Euler class of the obstruction bundle for Hilb 2. Okay, so I definitely have to stop here. I'm really sorry, but it was a rough start, and thanks for